Welcome to the deep dive. Today, we're tackling data structures and algorithm analysis in C++.
Oh, this one.
Yeah, it's basically the Rosetta Stone for anyone who wants to write code that doesn't just work.
Right.
But like sings?
You're absolutely right. It's one of those texts that every computer science student grapples with,
Yeah.
but its wisdom applies way beyond the classroom.
Hmm.
Whether you're building an app, optimizing a database,
Yeah.
or just curious about the magic behind the digital curtain,
Yeah.
understanding these concepts can be a game changer.
Okay, so this book is dense.
It is.
It covers everything from the building blocks of programming in C++ to mind-bendingly complex data structures and algorithms.
Yeah.
We've got recursion, classes, pointers,
Right.
and then it throws us into the deep end with lists, trees, heaps.
It does.
It even touches on theoretical computer science topics like the class NP.
Oh, yeah. That's fun stuff.
It's a lot, but that's why we're here. We'll break down the essentials of each chapter, just
Yeah.
giving you the insights you need
Yep.
without getting bogged down in the weeds.
That's the plan.
Think of it as your express lane to data structure mastery.
Exactly. We'll highlight the need-to-know information, sprinkle in some memorable examples,
Yeah.
and by the end of this deep dive, you'll be thinking about data in ways you never imagined.
So the book kicks things off with a focus on recursion.
Mm-hmm.
It even has a whole section called A Brief Introduction to Recursion.
Right at the beginning.
Why is this concept given so much emphasis right off the bat?
Well, I mean, recursion is, I think of it as the elegant cousin of iteration,
Okay.
particularly powerful when you're dealing with data that has a naturally nested or hierarchical structure.
Mm-hmm.
Think of it as a function that calls itself, breaking a problem down into smaller, self-similar pieces
Yeah.
until it hits a base case and bubbles back up with the solution.
It's like those Russian nesting dolls.
Oh, yeah.
Each one containing a smaller version of itself
Yes,
until you get to the tiniest one.
exactly.
Yeah.
One of the classic examples is calculating the factorial of a number.
Mm-hmm.
Recursively, you define it as the number,
Yeah.
multiplied by the factorial of the number minus 1.
Right.
Simple, elegant, and perfect for situations where the problem structure lends itself to this kind of self-similarity.
The book also mentions a few design rules for working with recursion.
Oh, yeah.
Like assuming all recursive calls work correctly.
Yes.
That seems like a leap of faith.
It's not about blind faith, but managing the mental complexity of recursive solutions.
Okay.
When designing a recursive function,
Right.
you focus on the overall logic.
Yeah.
And trust that those nested calls will handle their part flawlessly.
Mm.
Otherwise, you get lost in the layers and miss the forest for the trees.
So it's like delegating tasks to a team you trust.
Exactly.
You don't micromanage every step. You focus on the big picture.
Precisely.
Yeah.
And speaking of delegation, the book dives into C++ specifics next,
Right.
especially classes, constructors, and accessors.
Yeah.
It's a dense section.
Yeah.
But what are the key takeaways here for someone already comfortable with C++ basics?
Yeah. It's easy to get bogged down in the syntax.
It is, yeah.
Yeah.
The key here is understanding how classes encapsulate data and behavior,
Okay.
almost like blueprints for creating objects.
Yeah.
Constructors are like the setup crew,
Yeah.
initializing objects when they are created,
Mm.
while accessors are the bouncers, controlling access to the data members within the class.
So classes are like those prefab tiny homes.
Oh, I like that.
They come with all the components and instructions you need to create a complete functional unit.
Perfect analogy.
Yeah.
And then you have pointers, references,
Wow.
and the different ways of passing parameters.
Mm.
These might seem like minor details,
Yeah.
but they have a huge impact on efficiency,
Okay.
especially when you're dealing with large data structures.
Why is that?
Think about passing a giant file around.
Okay.
Copying it every time would be ridiculously slow
Yeah.
and eat up tons of memory.
Right.
Pointers and references are like sharing a link to the file.
Okay.
Everyone can access the same data directly without creating duplicates.
And the book goes deep on L value and R value references.
Yes.
Which are apparently a big deal in modern C++.
Absolutely.
That's the significance there.
It's all about move semantics.
Okay.
A way to transfer ownership of resources instead of copying them.
Mm-hmm.
Imagine moving, instead of photocopying a stack of documents,
Right.
way faster and more efficient. It's a subtle but powerful optimization,
Yeah.
especially as data structures grow more complex.
Okay, I'm starting to see how these seemingly small details can have
Yeah.
a big impact.
Absolutely. And then there's the infamous Big Five.
Right.
Destructors, copy constructors, move constructors, and assignment operators.
Hmm.
These can make your head spin,
Yeah.
but they are essential for managing memory properly and avoiding nasty crashes.
Even if I'm not building my own data structures from scratch.
Especially then, it's about understanding how things work under the hood,
Right.
so you can write robust, efficient code.
The C++ section also covers C-style arrays and strings.
Yeah.
Even though C++ has more powerful alternatives like vectors and strings.
Right.
Why bother with the old school stuff?
It's like learning to cook over a fire before using a fancy stove.
Okay.
Understanding the limitations of those lower-level constructs
Yeah.
helps you appreciate the power and convenience of the higher-level tools.
Okay, so we've laid the foundation.
We have.
The book then jumps into the first major data structure,
Okay.
the list ADT.
Oh, yes.
What makes lists so fundamental?
Well, they seem pretty basic.
Yeah.
Lists are foundational because they represent a sequence of elements.
Okay.
Like your to-do list, a
Yeah.
playlist, or the steps in a recipe. They embody the idea of ordered data, which is surprisingly powerful.
Right. And the book distinguishes between the abstract concept of a list,
Yeah.
the list ADT,
Yeah.
and specific implementations like the STL's vector and list.
Right.
What's the difference?
The list ADT defines the blueprint, the operations you can perform on a list, like
Okay.
inserting, deleting, and accessing elements.
Right.
Vectors and lists are like different builders using that blueprint.
Okay.
They provide concrete implementations,
Yeah.
each with trade-offs in terms of efficiency and how they store data.
The book explains that vectors are great for random access.
Yes.
You can instantly jump to any element, but inserting or deleting elements, especially in the middle,
Yeah,
can be slow because everything has to shift.
that's right. That's right.
Why is that?
That's because vectors store elements in contiguous memory,
Okay.
like houses on a street.
Right.
To add or remove one in the middle, we have to move all the subsequent houses down the block.
Lists, on the other hand, are implemented using linked nodes, which are like houses with their own separate driveways.
Exactly.
You can easily add or remove a house without affecting the others,
Right.
but you lose that instant access to a specific address.
That's the trade-off.
Yeah.
And the book gets into the nitty-gritty of implementing both vectors and lists, which is incredibly valuable even if you're mostly using pre-built versions from the STL.
It's like knowing how the engine of your car works.
Oh, yeah, yeah.
Even if you don't rebuild it yourself,
Yeah.
understanding the mechanics helps you diagnose problems.
Right.
And make informed choices.
Right. And speaking of making choices,
Okay.
the book introduces this concept of iterators.
Mm-hmm.
What did you make of those?
Iterators seemed like this powerful abstraction,
Yeah.
a way to traverse a list without
Yes.
worrying about its internal implementation.
Right.
It's like having a universal remote control that works with any TV,
I like that.
regardless of the brand or model.
Precisely.
Yeah.
Iterators let you write generic reusable code that can work with different kinds of lists without having to rewrite everything from scratch.
Yeah.
It's a key part of what makes the STL so powerful.
Okay, after lists, the book jumps into stacks and queues.
Oh, yes.
These seem like more specialized data structures.
They are.
Where do they fit into the picture?
Stacks and queues are like lists with strict house rules.
Okay.
Stacks are LIFO,
Mm.
last in, first out, like a stack of plates. You can only add or remove from the top.
Yeah.
Queues are FIFO,
Okay.
first in, first out, like a line at the bank.
Yeah.
First come, first served.
So a stack is like the undo function in a text editor.
Oh, yeah.
The last action you took is the first one reversed.
Yes.
And a queue is like managing print jobs.
Right.
They're processed in the order they were received.
Exactly. These restricted access patterns make stacks and queues perfect for certain tasks.
Yeah.
Stacks for tracking function calls, parsing expressions, undoing actions. Queues for managing tasks, simulating real-world scenarios, handling requests in order...
The book presents different ways to implement stacks and queues using arrays or linked lists.
Right.
Does that affect how they work?
The underlying implementation doesn't change their core behavior.
Okay.
They still follow the LIFO or FIFO rule,
Right.
but it affects their performance characteristics, like how fast they are for different operations
Right.
and how much memory they use.
So an array-based stack might be faster for small stacks,
Yeah.
but a linked list-based stack could be more efficient for really big ones.
Exactly. The choice depends on your specific needs.
Yeah.
And then there's this thing called stack overflow,
Okay.
which sounds scary.
Yeah, like something that makes your computer explode.
Not quite, but it can crash your program.
Oh, okay.
Stack overflow happens when you try to push more onto the stack than it can hold.
Yeah.
Usually a sign of runaway recursion where a function keeps calling itself endlessly.
So it's like trying to fit an elephant into a shoebox.
Precisely.
Okay.
It's about being mindful of the limitations of the data structure
Mm-hmm.
and ensuring your code doesn't push it past its limits.
Speaking of pushing limits,
Okay.
the book uses this cool example of evaluating postfix expressions with stacks.
Oh, yeah.
What are those, and how do stacks make them easier to work with?
Postfix expressions, also called reverse Polish notation,
Mm-hmm.
are a way of writing mathematical expressions where the operator comes after the numbers it's operating on.
Okay.
So 3 plus 4 becomes 3, 4 plus backs.
It's like writing sentences backwards.
Yeah, kinda.
Why would we do that?
It eliminates ambiguity and makes evaluating expressions super easy with a stack.
Okay.
You scan the expression, push numbers onto the stack,
Right.
and when you hit an operator,
Yeah.
you pop the top two numbers,
Like it.
do the operation, and push the result back on.
Okay.
At the end, you're left with the final answer on the stack.
So the stack is like a temporary workspace
Exactly.
where we manipulate the numbers as we process the expression.
It's an elegant solution that shows the power of stacks for parsing and evaluating expressions.
Okay, I think we've covered stacks and queues pretty well.
I think so.
Now, on to a completely different type of data structure, trees.
Ah, yes. Trees.
Yeah.
They're a whole different way of organizing data.
Right.
Not linearly like a list,
Yeah.
but hierarchically.
Yeah.
Imagine a family tree or the file system on your computer.
Makes sense.
Yeah.
So we're moving beyond simple lists
Yeah.
and getting into more complex structures.
That's right.
So we're branching out from linear structures like lists into something more hierarchical with trees.
That's right. Instead of a simple sequence, we have this beautiful branching structure with a root, branches, and leaves,
Right.
just like a real tree.
I'm definitely picturing that family tree analogy.
It's a perfect fit. And just like family trees show relationships, trees in computer science are used to represent hierarchies in so many areas.
Right.
File systems, organizational charts, even the structure of a web page.
The book starts with general trees, where a node can have any number of children, but then quickly focuses on binary search trees.
Yes.
What makes them so special?
Binary search trees have this incredible property that makes them incredibly efficient for searching and sorting.
Yep.
For any node, everything to its left is smaller,
Right.
and everything to its right is larger.
Gotcha.
The structure itself encodes an ordering.
So it's like a built-in sorting mechanism.
Exactly. But there's a catch.
Okay.
The tree has to be built correctly.
Right.
If you insert elements randomly, it can become unbalanced,
Yeah.
looking more like a wonky, lopsided list than a proper tree.
And that defeats the purpose, right?
Yeah,
It
exactly.
would be as slow as searching a regular list.
You got it. That's where balanced search trees come in.
Okay.
These clever structures automatically rebalance themselves as you insert or delete elements, ensuring quick search times even in the worst-case scenario.
The book delves into AVL trees, a type of balanced search tree.
Yes.
Gets pretty complex with rotations and height calculations.
Yeah.
Is it worth understanding all that if we're mostly going to use pre-built libraries?
Even if you're not building them from scratch.
Yeah.
Understanding the concepts behind AVL trees or other self-balancing mechanisms can help you write better code.
Okay.
It's like knowing the rules of the road even if you're using a GPS.
Right.
It helps you make informed decisions.
So it's about the bigger picture, not just the specific implementation.
Exactly. Now, shifting gears a bit, the book also mentions B trees,
Okay.
which are designed for a different environment,
Yeah.
storing data on disk rather than in memory.
So this is where things get really practical.
Absolutely.
We're thinking about how data is physically stored.
B trees are optimized for situations where data is too large to fit in memory all at once, like databases or file systems.
Right.
Their structure minimizes those expensive disk accesses.
It's like having a well-organized library.
Oh, yeah.
You don't have to pull out every book to find the one you need.
Perfect analogy. And speaking of well-organized libraries, the book shows how trees can be used to implement sets and maps.
Right.
Incredibly useful data structures for storing collections.
Okay, remind me, what are sets and maps again?
Think of a set like a bag of unique marbles.
Okay.
No duplicates allowed.
Right.
A map is like a dictionary. It stores key value pairs,
Right.
like words and their definitions.
So how do trees fit into this picture?
Both sets and maps can be implemented using binary search trees.
Okay.
For a set, you just insert each element into the tree,
Mm.
and the tree's structure guarantees no duplicates.
Right.
For a map, the key becomes the value of the node,
Yeah.
and the associated value is stored alongside it.
So we're leveraging that ordered structure again to efficiently search for keys
Exactly.
and retrieve their values.
And because search times in a balanced binary search tree are logarithmic, operations like insertion, deletion, and retrieval are super fast.
It's amazing how a simple structure like a tree can be so versatile.
It really is. Now, let's move on to a completely different approach to storing and retrieving data. Hashing.
Hashing. That sounds like something you do to potatoes.
It might sound that way, but in computer science, hashing is about mapping keys to specific locations in a table.
Okay.
Almost like assigning a unique address to each element.
So instead of relying on an ordered structure like a tree,
Right.
we're using a function to calculate where an element should live in this table.
That's the gist of it.
Okay.
The goal is to spread the keys evenly to minimize collisions.
Right.
Situations where two keys map to the same location.
Like when two people have the same birthday.
Exactly.
What happens then?
That's where collision resolution techniques come in.
Okay.
Like separate chaining, which is like having multiple people with the same birthday share a cake.
Okay.
Or open addressing, which is like finding a different open seat in a crowded movie theater.
So we have strategies for dealing with these birthday collisions in the table.
Exactly. The book goes deep on different techniques and how they impact performance. The cool thing about hash tables is they can offer near constant time performance for operations like insertion, deletion, and retrieval.
That sounds incredibly efficient.
Yeah.
Is there a catch?
The catch is maintaining that performance as the table fills up.
Okay.
Techniques like rehashing and dynamic resizing come into play,
Right.
which is like moving to a bigger house when your family outgrows the current one.
So it's about managing the table size and ensuring it doesn't get too crowded.
Right. And choosing a good hash function is crucial.
Okay.
A bad one can lead to clustering,
Right.
where lots of keys map to the same location, making the table inefficient.
So it's not as simple as just throwing everything into a table and hoping for the best.
There's definitely an art to it,
Yeah.
but when done right, hash tables are incredibly powerful.
Yeah.
The book also talks about unordered sets and unordered maps,
Okay.
which are basically hash table implementations of the sets and maps we talked about earlier.
So if you don't care about the order of elements, you can potentially get even better performance with these unordered versions.
Exactly. It's all about choosing the right tool for the job.
Okay.
And speaking of specialized tools, the book delves into some advanced hashing techniques like cuckoo hashing and hopscotch hashing.
Cuckoo hashing.
You've ever heard of those?
They sound like exotic bird dances.
Well, they're a bit more complex than your typical hash table,
Yeah.
but they aim to improve worst-case performance,
Right.
ensuring lookups stay fast even when the table is packed.
So like having a super efficient filing system that never slows down, even with tons of documents.
Exactly. And then there's universal hashing,
Right.
which is like having a whole arsenal of hash functions ready to handle any data set you throw at it.
Wow.
The goal is to minimize collisions no matter what the input looks like.
Okay, I'm starting to feel like a hashing expert. The book even revisits that word puzzle problem from earlier chapters,
Oh.
showing how hashing makes the solution much faster.
That's a great example of how choosing the right data structure can make a huge difference. Remember, the original solution involved checking every possible word against a dictionary,
Right, which was super slow.
which was super slow.
But with a hash table,
Right.
we can do those dictionary lookups in practically no time, making the whole process much faster.
It highlights the importance of understanding your options and picking the best tool for the job.
Okay, so we've hashed that out pretty thoroughly. Now let's move on to a different kind of data structure. Priority queues.
Oh, yes. Priority queues.
What are those all about?
Priority queues are a bit like lines at an amusement park, but with a twist.
Okay.
Instead of everyone waiting their turn in a first-come, first-serve order,
Right.
people with fast passes get to cut in line.
So it's about prioritizing certain elements over others.
Exactly. Imagine a hospital emergency room. Patients with the most urgent needs get seen first, regardless of when they arrived.
Right.
That's the essence of a priority queue.
That makes sense. I
Mhm.
can see how they would be useful in all sorts of situations.
Yeah.
Task scheduling, event simulation, anything where some items need to be handled before others.
Absolutely. The book dives into different implementations like binary heaps, binomial queues, and even something called leftist heaps.
Okay.
Each has its own performance quirks and trade-offs.
Binary heaps seem to be the most common.
They are, yeah.
They're based on a complete binary tree,
Yes?
where the parent node is always greater than or equal to its children, right?
That's right. The heap property ensures that the element with the highest priority is always at the top,
Right.
making it super fast to retrieve.
And the book explains how to do things like insert elements, delete them, and find the minimum, all while maintaining that heap property.
It's like having a well-organized pile of gifts.
Okay.
The most exciting one is always on top.
Yeah.
And when you take it, you rearrange the pile to keep the next best one at the ready.
Okay, that makes sense.
Yeah.
The book mentions this selection problem, finding the Gelf smallest element in a collection.
Yes.
Apparently, priority queues can help with that.
They're perfect for it. You just insert all the elements into the priority queue
Okay.
and then keep removing the minimum element 8 times.
Right.
The Gilth one you remove is the answer.
So the priority queue automatically takes care of finding and removing the smallest elements until we get to the one we want.
That's exactly right.
That's pretty slick.
It highlights the power of having the right tool for the job.
Right.
And then there are Fibonacci heaps, which are even more specialized
Okay.
and offer crazy good performance for certain operations.
Fibonacci heaps.
Yeah.
Those sound familiar from math class.
Uh-huh.
Are they related?
They are. Fibonacci heaps are complex,
Yeah.
but can achieve something called amortized constant time for certain operations,
Okay.
meaning that on average, they're incredibly fast,
Right.
even though individual operations might occasionally take a bit longer.
It's like saving up time on the easy tasks to compensate for the occasional harder one.
Exactly.
Yeah.
And in applications where those specific operations are crucial, Fibonacci heaps can be a real game changer.
Okay, we've explored heaps and priority queues quite a bit.
Yeah.
Now, let's get into something I think everyone has heard of, sorting algorithms.
Ah, yes.
Yeah.
Sorting,
Yeah.
one of the most fundamental and well-studied problems in computer science.
It's everywhere.
From arranging contacts in your phone
Yeah.
to organizing search results, sorting is everywhere.
Yeah.
And the book takes us on a tour of the classics.
It starts with insertion, sort,
Mm-hmm.
which seems pretty intuitive.
It is, yeah.
You take each element and insert it into its correct position in the already sorted part of the array.
Insertion sort is like sorting a hand of cards.
Okay.
You pick up one card at a time and insert it into the right spot.
Yeah.
It's easy to understand and quite efficient for small data sets.
But I imagine it gets slow when you have a lot of things to sort.
That's right.
Yeah.
The book analyzes its time complexity, and it's O(n)(2 in the worst case.
Right.
Which means the time it takes can grow quadratically as the number of elements increases.
Yeah.
For large data sets, we need something more powerful.
And that's where shell sort comes in, right?
Exactly.
It's like an upgraded version of insertion sort.
Shell sort improves upon insertion sort by comparing elements farther apart, gradually reducing the gap. It's like sorting a deck of cards by first arranging all the hearts,
Okay.
then all the diamonds, and so on,
All right.
before doing a final sort within each suit.
So it's like pre-sorting the elements to make the final sorting process faster.
Exactly. And then the book introduces merge sort,
Okay.
which uses a completely different strategy called divide and conquer.
Divide and conquer. Sounds like a military tactic.
Well, it's quite effective in sorting, too.
Yeah.
Mergesort recursively divides the array into smaller subarrays,
Okay.
sorts them, and then merges the sorted subarrays back together.
Gotcha.
It's like splitting a big problem into smaller, manageable tasks, and then combining the solutions.
The book describes it as a dance of splitting and merging,
Oh, yeah.
which is a lovely visual.
I like that.
And its time complexity is O(n) log n.